Hi guys, so like I said, we're going to get into equilibrium problems that are a little bit more complicated where you can write out the KEQ, but they're really not going to give you any numbers to plug in. They're not going to give you the concentrations of all of the reactants and the products at equilibrium. So you have to do some stuff to figure that out first. So these tables here are called ICE tables, and they're called ICE tables because you're going to have an initial concentration of your reactants. Before the reaction starts, you don't have any products. Then we're going to look at how those concentrations change until you finally have a reaction that's in equilibrium. Okay, so basically, like, there's a lot of different ways they can give you information for you to use these tables. So for this question, if I look at what I'm given, I have 0.2 moles of A in a 2-liter flask. So if I have 0.2 moles, and that's in a 2-liter flask, when I divide those two numbers, what am I solving for? I'm solving for molarity, which is concentration. So in a roundabout way, they gave me the concentration of the reactant. I'm going to just draw a line here to keep my reactant side and my product side separate. Okay, so you're always going to start off with 0 molarities for your products because, like I said, we didn't start making them yet. Okay, now the change is what's going to happen as reactants start to turn into products as the reaction goes. So guys, think about it. If reactants are turning into products, what's happening to the amount of reactants? They're going down. So your reactants are always going to have a negative change. Now the products, you're making them, so they're always going to go up. They're always going to have a positive change. Okay? And we don't know exactly what that change is, so we're going to use an X to represent what that change is. But you also have to take into consideration what the coefficient is. So the change for A is not just going to be minus X, it's going to be minus 2X. Okay? B2, and C2, they both have coefficients of 1 when you look up at the balanced equation. So you never need to write the number 1. So I'm just going to do plus X and plus X. Okay? All right, so now your equilibrium concentration, that's taking your initial concentration and your change. So for A, for reactant A, I had 0.1 to start with, and I'm going to minus 2x. For B2, 0 plus x is just x. And for C2, 0 plus x, again, is just x. Okay? So now, guys, if I have some way to solve for x, then I can figure out what the concentrations of the reactants and products are when I'm in equilibrium and eventually get my KEQ, which is what the problem is asking me to do. Okay, so let's write out what the KEQ should be. I have my products or my reactant, and my reactant has 2 in front of it, so that means it needs to be squared. Okay, now all I have to plug in here are I have X from my ICE table. That's what the concentration of B2 is going to be. The concentration of C2 is going to be X. And the concentration of A is 0.1 minus 2X. And this whole thing is going to be squared. Right? Okay. So now what I can actually do first is solve for X. And if I do that, I need to look at what they gave me in the problem. Okay? They're telling me that A, when at equilibrium, is supposed to be equal to 0.078. That means that this is equal to 0.078. So if I know that, I can solve for x. So x equals 0.011 molar. Okay? Now that I know what x is, I can throw that number into this equation. So guys, it would be good just for practice if you can plug that 0.011 into here everywhere you see an x and solve it, and then we'll see if we got the same thing. So when I did it, I got 0.02. Okay. So let's look at, we'll look at two more together, and then I'm going to give you guys some to practice on your own. Okay, so I like to always separate. I have reactants and products, so I like to do that in my ICE table too. Here are my reactants, here are my products. Okay. So now this one is telling us we're starting off with 1 atm of each reactant. So that's nice. I know what I'm starting with there and there. And as always, my products, I didn't make any yet, so I have 0. Okay. Just like the problem we did before, guys, they're telling me that my oxygen, when I'm at equilibrium, that my oxygen is going to have a concentration of that. So I know that whatever I put in this box, it's going to have to be equal to that number. So again, guys, just like the one before, that's going to help me solve for x. All right, let's look at my change. My reactant side is turning into products. So my reactant side is always going to go down. My product side is always going to go up. What is it going to go down by? Whatever the coefficient is. Okay. If I continue this, I mix together those two. Okay. So there we go. So if I solve for x right here, 1 minus x equals 0.506. So if I get x by itself, I get x equals 0.494. Okay, so now that I know what x equals, I can plug that in here, and I can plug that in here. And when I do that, I get 0.012 for my NO, and I get 0.988 for my N2. So the question didn't ask me to find the concentrations of everything at equilibrium. Again, it asked me to find KEQ. So you don't want to stop here. I'm going to write out the KEQ for this problem. Alright, so I have my products, NO2, and it's got a coefficient of 2, so I have to square that. And I have my reactants, NO also gets squared, and O2 has a coefficient of 1, so I could leave that alone. Alright, so now that I know that, guys, and I solve for all my concentrations, I can just go ahead and plug that stuff in. So NO2 was 988 squared. The concentration of NO was 0.012 squared, and the concentration of O2 is 0.506. They gave that to me. And when I solve, I get that. So this number is definitely way bigger than 1, which means what? It means that my products are more than my reactants. So it means that my my forward reaction is favored. Okay. One more we'll look at. So guys, and this one's a little bit tough because look, they don't give me the reaction. They just say that HI is decomposing. So when HI breaks apart, it breaks into hydrogen and iodine, which are its elements. I have to make sure the equation is balanced. So to do that, I'm going to put a 2 there. They're telling me my moles and my liters of HI. So if I divide those two numbers, I get the molar of HI. My products always start off at 0. I'm going to do my change. Okay. And then I'm going to do all together my initial and my change. Okay. All right, so this problem again is a little different because they're giving me KEQ. They're asking me to find concentration. So right now I can't solve for X because I don't know what it is. I have to think about my KEQ. I have to do my products over my reactant, okay? And I have to literally plug in what they're giving me. So 1.23 times 10 to the negative 3 is my KEQ. H2 is X, I2 is X, and my bottom number is 0.24 minus 2X. So this looks like it's going to be a little bit messy, but before I let it get crazy, let me show you. I'm just going to rewrite it so that it makes sense. When you have X times X, that's the same as X squared, yes? So I have two things that are squared on this right side of the equal sign. How do I get rid of something that's squared? I take the square root. Now I can get rid of that. So the square root of this number is 0.0351, and now I just have X over 0.24 minus 2X. I got rid of all my squareds. Okay? When I solve for X, I get 0.0079. Okay? Now H and I are equal to each other in concentration. They're both X. And see, they're both X. And I just solve for X. So I know that they both have a concentration of 0.0079 molar. If I look at my concentration of HI, if I scroll back up, my concentration of HI is 0.24 minus 2 times X. And when I solve for that, I get 0.224 molar. So those are my answers there. If you guys want to stop here and give page 5 a try, that would be great. All right, see you for the next one.